There's this fascinating legend about Michelangelo. He finishes this incredibly lifelike sculpture of Moses, right? And he's just so completely captivated by how real it looks that he literally strikes its marble knee with his hammer and yells at it to speak. It's a wild story, but it really hits the nail on the head about human nature. We have always seen language as the absolute ultimate proof of humanity and sentience. From ancient myths of statues coming alive right up to modern sci-fi, we just have this deep-seated obsession with building something from scratch and then, well, having a conversation with it.
The explainer, demystifying large language models. Okay, let's dive right in. Today, in this explainer, we are completely flipping the script on how we look at these systems. We really need to stop viewing them as these magical, sentient black boxes and start seeing them for what they actually are: ridiculously sophisticated, high-powered word predictors. I promise, it's not magic, it's just math. And by the end of this, you're going to see exactly how the whole shebang works. How much do we know at any time? Much more, or so I believe, than we know we know. I absolutely love that Agatha Christie quote. And honestly, it is the perfect lens for what we're digging into today. Because think about it. When you and I process language, we are pulling from an enormous well of hidden knowledge without even realizing it. And modern neural networks, they basically do the exact same thing. They're just uncovering and using these massive, hidden statistical relationships that are already buried deep inside human language.
Large Language Model, or LLM, a computational agent designed to interact conversationally with people by predicting the next word. So yeah, at their absolute core, that is literally all they are doing, predicting the next word. Now look, I totally get it. It's human nature to want these tools to be alive. I mean, back in the 1960s with Eliza, the very first chatbot, people were spilling their deepest personal secrets to a super basic script. But if we pivot back to objective reality here, an LLM is simply a mathematical engine calculating the very next token in a sequence.
So the big question is, how does this engine actually learn all this stuff? Well, think about how a little kid learns. Children pick up something like 7 to 10 new words every single day, largely just as a byproduct of reading and absorbing context. They aren't sitting there memorizing the dictionary. Large language models learn in a shockingly similar way. Through a phase we call pre-training, they literally map out the entire world just by iteratively predicting tokens across a mind-bogglingly massive amount of text. It's basically like playing the world's most massive game of fill-in-the-blank, millions of times a second. If the model reads, "With roses, dahlias, and peonies, I was surrounded by," and it has to guess flowers, boom, it just learned an ontological fact. If it predicts the end of "the room wasn't just big, it learns that enormous implies a much greater scale. It learns math by finishing "the square root of 4 is," and history by guessing authors of famous books. Just by constantly predicting, the system absorbs logic, scale, and hard facts. It's wild.
Now check this out. This is where the literal math happens. Based on just a short piece of input context, the transformer model calculates the exact odds. It says, okay, there's a 44% chance the next word is all, a 33% chance it's the, 15% for your, and so on. It is quite literally generating a mathematical probability distribution for every single possible word in its entire vocabulary every single time.
The autoregressive loop. 1. Read the input context. 2. Predict the probability distribution. 3. Sample the next word. 4. Add the word to the context and repeat. This is the core engine right here. This is how a machine writes a 5-page essay. It happens one single token at a time in a continuous loop. It reads the context, does the math we just talked about, picks a word, and this is absolutely crucial. It takes that brand new word, glues it to the end of the context, and does the whole thing all over again.
Watch how this actually builds in real time. The model guesses the word all and immediately loops that exact word right back into its own input string. So now the context is just a little bit longer. Based on that newly updated context, it makes a fresh guess, in this case, the. The model is constantly conditioning its next guess on the very words it literally just generated a millisecond ago. It's just a relentless, high-speed, left-to-right generation cycle.
Okay, zooming out for a second, just to put this in perspective with the broader AI landscape. There are basically 3 architectural flavors out there. You've got encoder models, like BERT, which look at text bidirectionally to classify things. Then there are encoder-decoder models. These map one sequence to another, which is perfect for translating English to French. But our conversational chatbots, the ones we use every day, like GPT or Claude, those are decoder architectures. They strictly flow left to right, and their sole purpose is just generating novel text, token by token. Conditional generation, generating text token by token, conditioned on an input prompt. All right, let's shift from the back-end mechanics to what you and I actually experience. Everything we do with these models is conditional generation. And this is where we step into the driver's seat. We steer this massive engine with our prompts. We hand the model a starting condition. Maybe it's a question, a command, a half-finished sentence, and we're basically asking it to keep generating text based specifically on what we just handed it.
Let's look at this Python example. Instead of just asking the model a programming question blindly, we can use a really clever trick called few-shot prompting. We literally provide a labeled demonstration right inside the prompt. By showing it a sample computer science question and the correct answer first, the model instantly learns the format and the logic we want right there in context. We aren't reprogramming the model or changing its underlying weights at all, we're just giving it a super structured context to guide its immediate statistical predictions.
The role of system prompts. Silently prepended to user text, defines the task, sets the tone, establishes rules. But here's a crazy detail. Before you ever even type hello to a chatbot, the model has already been given a massive set of instructions. It's called a system prompt. It's this hidden instruction manual silently tacked onto the front of your text. It tells the model, hey, you are a helpful assistant. It sets the vibe to be warm or professional, and it lays down hard rules like avoiding dangerous content. It completely frames the mathematical context before the conversation even kicks off. Logits to probabilities. The internal network generates real-valued scores called logits, which are converted into percentages by the softmax function. All right, we're getting to the absolute climax of how this thing decides what to say. Inside the network, the raw output is not some clean, easy percentage. It's actually a list of raw, messy mathematical scores called logits. To actually use these scores, the model passes them through a function called softmax. Softmax normalizes those raw logits into a beautiful, clean probability distribution. It takes raw math and turns it into that perfect list of percentages that perfectly add up to 100. Greedy decoding versus random sampling. So once we have our percentages, how do we actually pick the word? Well, it's a classic Goldilocks situation. If we use greedy decoding, we just pick the highest probability word every single time. The catch? It is incredibly boring, robotic, and super repetitive. On the flip side, we could use random sampling and just completely roll the dice. But that is way too chaotic. You risk grabbing rare, weird words from the absolute bottom of the barrel, and the sentence just goes completely off the rails into hallucination territory. Temperature sampling, a decoding method that reshapes the probability distribution by dividing the logits by a temperature parameter before applying the softmax function. To fix this whole problem, researchers found the porridge that is just right, temperature sampling. It's a brilliant little trick that tweaks the math to find that perfect sweet spot of conversational creativity. Before applying that softmax function we just talked about, the system simply divides those raw logits by a specific number, which we call the temperature parameter. Lower temperature equals sharper distribution. Higher temperature equals flatter distribution. Tweaking this one single dial completely changes the personality and reliability of the output. If you drop the temperature, say below 1, dividing the math makes the high probabilities even higher. The distribution gets super sharp, safe, and highly focused. But if you raise the temperature, the math flattens out. The odds become much more equal, which means the model is way more likely to pick diverse, creative, and totally unexpected words. You are literally turning a dial on the machine's creativity. Which brings us to a pretty wild thought. We started this explainer talking about a magical, sentient machine, but as we've seen, it's actually an autoregressive loop running softmax and temperature parameters to just mathematically guess the next word. Which leaves us with this final, slightly provocative question. If the magic of a large language model, which can write poetry, pass the bar exam, and even comfort us, is ultimately just finding the perfect statistical temperature to predict the next word, what does that reveal about the hidden mechanics of our own daily human conversations? Definitely something to chew on the next time you're chatting with a friend. Thanks so much for joining me on this explainer, and I will catch you in the next one.